We are going to learn how to name alkanes, alkenes, and alkynes using the official IUPAC system. To keep it simple, we use a two-step approach. Identify the parent molecule, the main backbone. Then name and locate the substituents, the branches. Let's dive right in with our first example. Naming alkanes, single bonds. Take a look at the structure. First, we need to find the parent molecule, the longest continuous chain of carbon atoms. You should count from here. Not there. The longest chain contains 7 carbons. It is a heptane. Finding this parent backbone is always your essential first step. Next, look at what is hanging off that main chain. We have 3 substituents, 1 chloro group, 2 methyl groups. To tell someone exactly where these groups are, we need to number the carbons in the parent chain. So chloro is at 2 and 2 methyls at 3 and 5, respectively. The final IUPAC name is 2-chloro-3,5-dimethylheptane, where the 2 locates chloro, the 3 and 5 specify 2 methyls. We use the prefix di to show there are 2 identical groups. We separate numbers with commas and numbers from words with hyphens. Note that we list the substituents in alphabetical order, ignoring prefixes like di. Because C comes before M, chloro goes first before methyl. Now, when we number carbons, we have 2 options of which side we start counting from. From right to left, as we just did, the 3 substituents land on carbons 2, 3, and 5. If counting from left to right, they land on carbons 3, 5, and 6. Here is the golden rule. We must always choose the numbering direction that gives our substituents the lowest possible numbers at the first point of difference. In this case, this is the first point of difference. 2 is smaller than 3. Counting from right to left is the correct path. Naming alkenes, double bonds. Now let's spice things up. What happens if we introduce a double bond? The moment a double or triple bond enters the picture, the rules change slightly because functional groups take priority. In this alkene structure, the longest chain, the parent, containing both carbons of the double bond is 6 carbons long, not 7. It's a hexene. Forget about the substituents for a second. The double bond gets the absolute lowest number possible. Counting from the right puts it at carbon 5. Counting from the left puts the double bond at carbon 1 and lower. We choose the left side. Numbering from the left puts our substituents at 5 for chloro, 2 for ethyl, and 4 for methyl. When naming the substituent, remember to use chloro rather than chlorine. The final name, 5-chloro-2-ethyl, 4-methyl, 1-hexene. Let's look at the structure, where we have a triple bond. The priority rules here are exactly the same as they are for alkenes. The triple bond takes precedence for numbering. Our parent chain contains 7 carbons and includes the triple bond, making it a heptane. Numbering from the left gives the triple bond the lowest number carbon 1. This leaves our substituents at 6 for chloro, 3 and 5 2-methyls. Final name is 6-chloro-3,5-dimethyl, 1-heptane. For cyclic molecules, the ring portion itself becomes the parent molecule. Look at this structure, which is a 5-carbon ring with a double bond, cyclopentene. In a cyclic alkene, the 2 double-bonded carbons are always automatically assigned positions 1 and 2. Your job is to decide which of those 2 carbons is 1 and 2. To do that, choose the direction that walks through the double bond and hits the closest substituent with the lowest possible number. If we start at this double bond carbon as number 1, the other one is 2, and count counterclockwise, we will put carbon 3 for the methyl group. Apparently, it is the lowest one. Going in the other direction would put 5 for the methyl. Final name is 3-methylcyclopentene. Because the double bond in a simple ring is always at position 1, you don't even need to write the 1 for the double bond.